Thank you. I feel like I should know this, Yana, a little better. Um, okay, cool. Let's talk. So Gonzalo said that I do a lot of machine learning, and I do. Um, Generically, we try to convert English or amino acid sequence into some machine that will tell us things or make things. Not really clear yet how this is going to work out in the end. But I'm not going to talk about that. Sorry. So if you're waiting for it, this is not going to happen. I'm going to talk about something a lot less uh, advanced or technical, and I hope you forgive me. And if you're interested in the other stuff, just come and talk to me. Okay. This is Earth about 4.5 billion years ago, right? At least we think that's what it looks like. It's a scientific comic, so please don't complain if it's not true and you know it. Then something happened. Namely, we got life, and Earth became this. So if you're thinking about the images that you get from space, this is what you get, right? And that is the impact of life. This is not something else. It didn't happen by itself. This is really, we got life, came with oxygen, we got these clouds, all of this wonderful stuff that we now call home on this planet is life, right? So it's a sort of a circle. We needed this for life, and now that life is here, we made it this way. We being the bacteria, of course, not us. I'm going to talk a little bit about the beginnings of the story of origins of life. It's actually a lot earlier than I ever imagined. So I started working on this project about 8 years ago, and I learned about this guy. This is Alexander Oparin. At the ripe old age of 30, for those of you who are younger in the audience, this is the time to do it. At the ripe old age of 30, in 1924, in the middle of the wonderful Russian Revolution between two World Wars and so on and so forth, he says he developed a theory that life on Earth developed through a gradual chemical evolution of carbon-based molecules. And he said, life is a special, very complex form of movement of matter, but this form did not always exist, and it is not separated from inorganic essence by an impervious abyss, but rather it emerged from her, the inorganic essence, as a new property in the process of evolution of the world. He said that in Russian. That's my translation, so if you know it otherwise, please let me know. All right? Okay, so he basically says life wasn't created, life evolved from the organic matter. And it's very convenient when you're in the middle of the Russian Revolution processes, because the communists don't want to hear about God. They want to hear about how we evolved from carbon-based life forms. But regardless, Alexander Oparin was a champion in this type of thought. But he wasn't alone. So there's this other guy, you guys probably heard of him a lot more, Jack Haldane, right? So Jack Haldane, at about the same time, right, maybe a little bit later, 1929, talks about the primordial soup. By the way, Jack Haldane was 37. I feel like, there is this time to make ideas, great ideas that will live on in history, or I was going to say infamy, but no, just in history. So please put your ideas out there. Jack Haldane talks about the primordial soup, which is basically the same story as Oparin. We're talking about this ancient Archean ocean, right? And in this ocean, there's all the molecules that let us have life. And life evolves from those molecules. So how does it do that, right? And we asked this question, and the first thought that came to mind is that this ocean is full of metals, and life requires metals, right? So the reason life requires metals is because we need to do electron transfer. And what's the best way to do electron transfer? I mean, think about the wires in your house, right? They're metal. There is electricity running through. The best way to do it is with metal. Proteins and RNA, whatever your belief is on the origins of life from RNA world or protein world or both, right? They don't do a good job transferring electrons, right? But metals do. So whoever was the origin of life would have used metals in order to transfer electrons, in order to do whatever functions they need to do. And it's still the case. There is an argument that electron transfer is a frozen accident in evolution, right? And we know that, for example, for the simplest mitochondrial chain, you need 13 iron sulfur clusters to do this. You need iron for this. And if you start looking at geological records, you see that this is actually a very clear sort of background for all biological evolution that you can imagine. So Phil Bourne and Gustavo Cartana Anolis had talked about the Archean ocean and the atmospheric oxygen and the concentrations of metals, which are really relevant to evolution of life. So what you see here on the top is that atmospheric oxygen was very low in the beginning. So remember in that original slide of Earth, Earth does not have an atmosphere. It has no oxygen. It takes life to bring oxygen onto the planet. But for the first 2.5 billion years or so, so again, Earth is 4.5 billion years or so old, for half of Earth's life, at least, there is no oxygen on the planet, right? And then we have this great oxidation event. It's not a one-day thing. So the great oxidation event took a little bit of time, right? But it starts over here, here somewhere, right? 2.4 billion years ago. I would say that it probably lasts a little longer, but you see the oxygen amounts are increasing over here and then increasing again. And at some point we had too much oxygen and then the Earth burned, right? Because we can't work out what the right amount should be. But realistically, there is this change that's happening. So when we start out, we have lots and lots of metals. Over here, there's high iron, high manganese, high cobalt, high nickel concentrations, right? So if you want to do electron transfer using metals, you have all of that. Now, the moment that you start getting oxygen, iron begins to rust, right? That's unfortunate, right? So if you leave something out, it rusts. And Earth went through a few periods because of that called snowball Earth, where it would freeze and then warm over again, and so on and so forth. That's a different story. If you're interested, I would love to talk about it. But the idea is that when life had appeared, we had all of this metal to work with, right? Which we don't anymore. But if we had a frozen accident in evolution, right, that the folds that would have appeared for binding metal back then would still continue to bind the metals now. It's just it would be different metals at this point or different ligands, right? So that's the main point that I'm trying to make. So how do you study this? Well, we only can study this using the data that we currently have, the structures that we currently have. And I know Janet talked about how to study ancient evolution and structures yesterday. The citation I have is from Ross Doolittle. And if you're talking about 10% or less sequence identity, you need to look at structure. You can't do this from sequence, right? And if we're talking about 4.5 billion years of evolution, 4.2 billion years of evolution, and life probably didn't appear together with the planet, but with 4.2 billion years of evolution, we're definitely at less than 10% sequence identity. So we have to go into structure. And I think this is the reason that you guys invited me to give this talk, because this is really, the structure here is my biggest use of structure in the types of work that we do. Okay, so I'm gonna start with a little bit of a lab prehistory, now that you know the world prehistory. So I had a postdoc in my lab when I just started at Rutgers. His name was Stefan Sen, is Stefan Sen. Stefan used to work with Manfred Zippel, and he was very well aware of this method called top match for aligning protein structures, right? And we wanted to see if we can find a structural origin of life, right, of these metal binding folds. So take all the metal binding proteins in the PDB and try to figure out what would be the structural origin of these metals, of metal binding folds. Now, he argued that metals constrain immediate protein environment, right? So if you have a metal bound to a protein, he says up to 18 angstrom sphere around this metal center can be drawn to identify the amino acids which are relevant to this particular binding and to the activity of this protein. We settled on 15 angstroms. That seemed like a more manageable story. And he basically did that. He put a pin in the center of the ligand, right, for every metal binding protein, and then drew a sphere of 15 angstroms around it. And he did it for 3 ligands. We wanted to start low, I guess. He took the iron sulfur cluster, so iron sulfur clusters, so Fe2S2 and Fe4S4, and he took the hemes, right? And he said, let's see how many residues we can get that we can work with in order to look at alignments, right, of these structures. But we need to translate that to sequence. So there is going to be some structure sequence story here. So if you look at, this is in 2014, if you looked at all the PDB entries at that point that had iron sulfur clusters bound and heme bound, then you could see that for hemes and for Fe4S4s, the distribution was pretty normal shape, right? So that meant that there were some residues for heme at least, some spheres for hemes at least, that were about 60 residues in size. And for iron sulfur clusters, there were some spheres that were about 65 residues in size. So they're surprisingly similar, even though the hemes are much longer and much larger. They take up more space in that 15 angstrom sphere that I told you about, right? But then the amount of residues that that are bound to that heme or that bind the heme is actually not as much. The Fe2S2 has a slightly weird distribution, but we think it's because this is mostly due to the binding of the iron sulfur cluster towards the surface of the chain, which only gives you half of the sphere, so to say. Right? So in this particular picture on the left, what you see is that we're going to count only the residues that are in blue, and we're going to exclude the residues that are in green. So if you wanted to do this with just sequence, it would be discontinuous and you couldn't do it this way. But if you wanted to do it in structure, you can align structural pieces. Okay. So Stefan extracted all of these features, all of these spheres, and then he said, let's do an alignment, a top match alignment of all of these spheres. Now, this is a reminder for those of you who haven't used top match or haven't used it in a while. The score for top match D is computed as the sum of the query length and the target length minus 2 times S. And S is some number that combines spatial deviation and the number of aligned residues, right? So basically, what that means is that you can think of D as the number of unaligned residues in the structural space, right? So it's not exactly that, but you could think about it in that matter, right? So the idea was that we had these 60, let's say, residue spheres. So 2 of them aligning would be 120, right, on average. And then you would subtract whatever the number of spheres that aligned, twice that number, and you would get the number unaligned. So the higher the number, the higher the distance, right? So this is the result that he got out of this. It's a very interesting result. It's a weird picture, so it takes some time to sort of understand what's happening. But the left-hand side is Fe4 again, Fe4S4, Fe2S2, and hemes, right? And the idea is that the y-axis reflects the distance between the cofactors in alignment. So this is the part which is not actually used in alignment. You align 2 structures, protein structures, and then you look at the distance between the cofactors because of this alignment, right? And you could see that for all of them in the very beginning, let's say to about 35 residues or somewhere there in the first plot closest to me, there is a very low distance between the ligands, right? And it then explodes. So structural distance, which tells you how well these folds are aligned, is actually correlated in some way or related to in some way to the distance of the ligands, which is actually not used in alignment. So what that told me is that these coffee cups that we've evolved for holding the metals, right, these have somehow evolved to do the same, to place the coffee cup in the same location of the fold, right? So the metal of related folds actually goes in the same place, right? And that was a key observation. And we looked at the distributions of these alignments, and the right-hand side is really bad structural alignments at distance above 120 residues. And the left-hand side is all alignments. And what you see there is this, at the beginning on the left-hand side, is this huge peak, right? Where the ligand-ligand distances are very short, right? So for smaller, better alignments, ligand-ligand distances are short. And for iron sulfur clusters, we computed that it's 2.8 angstrom center distances, and 2.1 for Fe2S2s, and 3 angstroms for hemes that define whether the alignment is going to be good, right? And that's an interesting observation, but here's what it looks like. So these are two sets of alignments, right? So here on the left-hand side, the iron sulfur clusters are overlapping. Again, the knowledge of where the ligand is does not go into decision-making about the alignment of structures. It just happens this way, right? And that suggests that they're related somehow. So on the left-hand side, what you're seeing is that the iron sulfur clusters are overlapping. There's two there. You could only see one in this particular visualization. And on the right-hand side, or the further left-hand side over there, we are actually seeing that the distances are much larger. And even though the RMSD for the right-hand side is smaller than the RMSD on the left-hand side, we believe that this alignment over here reflects the actual alignment, right? Rather than one where you have these ligands further away. So we did this, and then we said, okay, so now what do we do with that? Right? Now we know this information. We can infer whether alignments between protein structures are good or not. And what does that do for our evolutionary story? So I had a brilliant undergraduate who has since gotten her PhD in math from Princeton and is a postdoc in Korea in discrete mathematics. So she really was brilliant, is brilliant. But she came and she said, okay, let me take all of the PDB structures and we're going to make all the alignments. And then we're going to look at sequence. And again, the reason I keep coming back to sequence is because you want to be able to apply some of these alignment methods for sequence count to talk about evolution, right, to build trees. And that's, so we are going from this particular alignment, which we inferred to be correct on the basis of ligand-ligand distances, right? And we're going to look at the sequences of the superimposed residues, right? So basically, here there's the isoleucine aspartic acid alignment in structure, which is at position 96 of the top sequence over there, right? And what we're seeing is that you can put the sequence letters onto the structure and get the sequence alignment out without having done any sequence alignment. This is just superimposition of the residues, right? And what Linda had shown, and this is truly in, I guess, the spirit of what Burkhard has been teaching me for a bit, is that you can relate the alignment length in the structure to the distance, to the sequence identity in a way that would describe whether the structure alignment represented structures where ligands were close to each other, right? So you can label a pair of structures as being positive, red in this image, or negative, blue in this image, on the basis of how well the ligands align, right? And then you can draw the curve through it. We call this curve the Sally curve. Don't ask me for what it stands for. It was a long time ago. But the curve is called the Sally curve. And if you're above the curve, this is a correct alignment. And if you're below the curve, it's an incorrect alignment. And you don't need ligands anymore. All you got to do is take the structure, align it to another structure, and you can compute this. And the performance of this curve is actually on the right-hand side over there. At 0, we got very high precision, so 95% precision at about 75% recall, right? So there is structure-based sequence signal that tells us something about metal binding. And that was the story here. This is the data that we used for developing this method, this line, for drawing this line. And what you're seeing here on the x-axis is the ligand-ligand distance of the fold. On the y-axis is the count of the pairs of folds that fall into this space. And the color is positive is red and negative is blue. And what you see is that most of the folds that are predicted by Sally to be correct tend to have lower ligands, right? That's the training data, not surprising. But here's the non-training data. So we looked at ion binding spheres and non-ion, non-training data, metal ligand binding spheres. And they all looked about the same. So ligands were still close together, right? But this is all same ligand. So iron sulfur clusters, ligand, and another iron sulfur cluster binding fold, right? So we wanted to know, can we apply it across? So do the spheres that bind hemes look like the spheres that bind iron sulfur clusters, or ions for that matter? And this is the distribution. And guess what? They still are close, right? This is different shaped ligands, right? So they're not going to be identical, but they're still very close. And in case you're curious what that bump is on the lower curve, lower plot over there, that's copper binding. So apparently copper binding is weird, and we still can't explain why you can allow for really large distances between coppers in the structure without changing the sequence. Okay, so this is all a long story to tell you how we computed distances, right? So we are now saying that we have a score to compute distances, and we can compare all PDB structures with these distances, all metal binding PDB structures with these distances, because at this point we didn't have Martin's speed up, so we could only do a few structures at a time. So we only looked at these 4,000 structures that we can identify, 4,500. Took us about 4 months to get all the alignments. It was fun. Okay, so this is the network, right? So the nodes are the spheres, these protein spheres. The edges are the Sally scores, right? And the color indicates what is the metal that's there, the metal ligand. The pink, I'm sorry, you probably don't see the distribution, but the pink is hemes, and the purple is manganese, and then the red is the ions, and so on and so forth. And what you see here is that there's a bunch of hemes on the left and a bunch of coppers on the right, and there is a manganese distribution in the middle, or an iron distribution in the middle. And that is just for prettiness sake. But what we wanted to do is to remove redundancy in this curve, in this plot. And the reason for that was that we like to determine structures of the same thing over and over and over again. So if we wanted to study evolution, we really needed to somehow figure out how to remove redundancy. We did. I'm not going to go through how, but we basically clustered folds and selected representatives, right? So for all intents and purposes, that was it. This is what the reduced representative network looked like. It's not as obviously separated, right? So they're all more or less together, still suggesting that there are a limited number of origins, right, of these folds. And what we saw is that actually this was a good way of doing it, because the Sally scores got significantly higher for the representative network, right? So the Sally scores got significantly lower for the representative network, right? So the blue versus the red. And so then we said, okay, well, we're studying evolution. We need to add some ages to here. And we identified using GTDB relative ages, we identified where the proteins that gave rise to these spheres fall, right, into the bacterial space. And for every fold, we could say, okay, these are the 3 places where the fold showed up. We would take the oldest one as a score, right? And so you can compute the distances between oldest representatives of the spheres. And then you could also get the last common ancestor of every set of representatives, right? And compare the distances between them. So we incorporated this information into the edges, and we had a new network that had both the distances between spheres in sequence space as well as ages of the putative organisms that had them. And then we did some network analysis, just because we could. We did minimum spanning trees. So the idea was I still can't build trees, right? So I still cannot say, okay, this is the tree, and this is the root of the tree, and this is the origin of life. So we built these minimum spanning trees to identify central nodes, with the idea that nodes that are central to most paths have much like ancestral nodes, right? I don't know when this happened. I don't know how, but these central nodes would be most ancestral. And what you see on the right is that we did thousands of these trees just to make sure that we're correct. And some of these came up on top, right? So that little piece on the right, those are the 21 folds that we've identified as being central to this network. How am I doing on time? 10 minutes? Okay. Okay, excellent. So without doing anything else, what we see is that these 21 spheres listed on the right are mostly oxidoreductases. Now, I know I told you that I believe that we needed metals for electron transfer, right? But I didn't plan for this. They just happened to be oxidoreductases in the middle, right? So that was an interesting finding. So we then said, okay, well, we probably didn't start from these 60 amino acid spheres. So how do we get to the origins of life? And then Gonzalo did some work, and we thought that it was a great idea to use his tools for this further analysis. So this is the sphere, right? And then what we're going to do is going to look for structural repeats of smaller structural fragments in these folds, right? So this is Gonzalo's tool. We did not know each other at that point, so there is no connection there. But what you can see here is that within this particular fold, you can identify these peaks, which are structural repeats, right? So pieces, building blocks, Legos of what this incomplete fold is made out of, right? And we can do this for every one of our 21 spheres because we believe them to be ancestral. And what we found, actually, is that Ariel Aptekman in my lab found that these 21 spheres produce 6 clusters of these tiles, of these small Lego building blocks, right? This is just the similarity of these tiles. And of course, 6 clusters is because we cut it off at that point, so it could have been more. But we used the silhouette coefficient analysis to say, okay, this is probably the best place to cut it. And so these are the tiles, right? So I'm sure none of you are surprised that it's primarily secondary structurally defined tiles, right? So we have helices and small pieces of helices and beta sheets, right? But these are the 6 clusters that we identified. And we also found them, again, probably not surprisingly to most of you, throughout the PDB. So not just metal binding sites, right? Not just metal binding ligands, throughout all of the PDB, right? And this is the distribution of the tile clusters, right? So each dot represents one representative of a tile cluster numbered on the display. And the y-axis represents the count, the number of times it appears in the PDB. And you can tell that the highest one here, the clusters 2 and 5, this is a reminder, 2 is that smaller helix over there, and 5 is the beta sheets over there. So again, probably not surprising. But then we said, okay, can we put any ages on these tiles, right? I'm still going towards this whole, how did the life appear? And at that time, Caetano Anolis's group had put ages on scaffolds. This was a real tour de force. They went through all the evidence in the literature, starting from 3.8 billion years ago of the record of beginning of life. So we have an actual chert rock in Australia that tells us that at that 3.8 billion years ago, we already had life, right? Full on life. And starting from there on, and the P loops at that point, the group actually assigned ages to the scope folds. And we said, okay, we're going to take those scope folds and we're going to compare how many times our tiles appear in those scope folds, right, to their age. And the y-axis represents the age. The root is at the bottom at 3.8 billion years ago. And there is, at about 0.8 distance to the root, is about 1 billion years ago, right? So this is actual ages that we've put on there. And we also added the count of how many times the tiles appear in the structures of these scope folds. And that's the x-axis here. And what you're seeing here is that in the lower right-hand corner, the oldest tiles, the oldest folds, tend to have really large numbers of tiles, right? Right there. And then the youngest folds are, or the younger folds, tend to be smaller, right? So we go from 27 tiles to barely 5 tiles, right? The scope folds are arranged by age. So what we thought is that, when life appeared, it just sort of threw everything together, whatever worked. Like, here are all these folds that we could use. Let's throw everything together, kind of like a kid who has a bunch of Legos and is just going at it. And then as it got refined, we got better and better, right? So it became less and less relevant to throw folds in. Then there is something that happened over here, right? And we're talking about maybe 1.51 billion years ago. So what happened there? Remember this? That was the oxidation event, the great oxidation event. At about that time, right? So of course, in millennia, you can't really say that was the moment that this happened, but that's where it looks like, right? And so it looks like we can trace evolution of Earth in evolution of life. And after having spoken to some geologists, they don't believe their rock studies. They say, your records are better than ours. Biology is a better record keeper than rocks are. So that was a mind-blown moment for me, and I'm bringing it back to you. Okay, and since I got this invitation to talk, I thought, okay, this paper came out a couple of years back now, so we should actually do what we started out with, right? We should probably, now that we have these tools that align structures really fast, find these alignments that were not metal. Right? And I had asked my postdoc, Prabhakaran, to do this. And what he found is that if we took these spheres that we identified as being central, right? Because remember, we can't select anymore based on metals. We need to look for things otherwise. And so if we took these spheres that we identified as being central, what you can do is you can align them to about 23,000 structures in the sequence-reduced set of PDB. So that's about half of PDB sequence-reduced at 95% sequence identity. So is it because, is half a lot or a little? If we're talking about origins of life, we should have been getting these everywhere, these spheres everywhere in every structure. On the other hand, it's half, so it's not very clear whether that number is a lot or a little. But we take it as a positive sign, right? Because maybe we need to think more about the alignment tools that we use for this type of analysis. But half of them did align, and aligned well. So that's the reduction there, right? So that's a good alignment. So it's a TM score of above 0.5 for, and a sequence identity of more than 5%. And so what we saw is that there is minimal difference in terms of TM scores of alignments of metal binding and non-metal binding structures. And the sequence identity is also minimally different between metal binding and non-metal binding structures. We are still working on the analysis, but here's for some instant gratification, a minimum spanning trees of spheres, of these spheres that we all align. And you see it's a much less colorful network because there are no metals bound in most of these things, right? So this is a representative network that has mostly non-metal binding spheres that has arisen from looking at alignments of metal binding spheres. So we're still in the process. I'll let you know within the next year or so with a paper how that worked. So conclusions, similarity across folds strongly suggests that transition metal ligand binding had a small number of common origins at the beginning of it. Early metal binding folds were most likely carrying out redox reactions that arose from the central folds. We can identify protein tiles, thank you, Gonzalo, that have been there since more than 3.8 billion years ago. I recently read a paper that says there was already an organism 4.2 billion years ago. I don't know, but that's the story. And we say that there are two types of tiles that are the building blocks of much of the known structural diversity. And so what we're working on is expanding this analysis to non-metal proteins. And right now it looks like they do have overlap and a lot of similarity. So I've been talking about the people who did this work as I was going along, but it was also the result of work of these people. These are three of my collaborators, Paul Folkowski, Vic Nanda, and Diego Ferreira, and a postdoc in my lab who did much of the coding, Max Miller. Okay, the funding was NASA and the European Commission and the Gordon and Betty Moore Foundation and the NSF. And as Gonzalo said in the beginning, my office space kind of looks like this, and I'm looking for you. So if you're looking for a job, please come. Thank you.
That was a wonderful keynote lecture, Yana. I'm very happy. I must say, as much biased as I am for Yana, our keynotes are democratically selected, so I have nothing to do with it. So.
Hi, Yana.
Hi.
Nice talk. You show something that looked like a circular permutation, where you show us the example of some
of the structural alignments.
Yes. And did you also get circular permutations with the newer, faster tools, or no idea?
So the tools actually do take spatial orientation into account, right? So the image that I showed you is not a permutation per se. It's two different alignments, right? So that where the ligand moves around, that's two different alignments, two different protein structures.
Okay.
Aligning.
Because the numbers were lower on
the numbers.
Right, than on the left, and then on the top, they were the opposite. So I think it's a circular permutation.
I'm then not sure what you're referring to. Let's see. The very beginning, right?
Almost. Yeah, yeah.
This.
You just passed it. Yeah, it was.
Not this?
No, not it.
Oh,
it was
okay.
That one.
Okay.
Yeah.
Oh, okay. It's not a circular permutation. All right, got it. Thank you. They are discontinuous. Residues do not have to be continuous in sequence to be aligned in structure. That's the story. So what was the question? 115 to 120. Yeah. Yes. Right. So, but structural alignment does not require you to. Right.
But I wonder if the newer tools, the fast tools,
they do.
Be able to find.
They do. I am still trying to figure out how much do we lose, but not by not being able to use top match, because I found top match to be wonderful. But yeah. Thank you.
And source closed, unfortunately.
Sorry?
And source closed.
Yeah.
I mean, the code is. One last question, please, brief.
Thank you, Anna. I have friends who are in this origin of life field, and they believe that there were at the beginning only maybe 10 amino acids, and there were some which were joined later.
Yeah.
So I was wondering, if you look at your tiles, what is the nature of the amino acids? Are they is there a signal that it would be just the hydrophobic ones, or?
That's a great point. The tiles are small, right? So we're talking about 10, 12 amino acids in length, which is great, which is what we were looking for. In the paper, we also compare them to Andrei Lupash's work, for example, where he looked at the tile, or not tiles, or smaller structural fragments. So they are conceivably in the range of size where they would arise by chance, right? So origins of life, they have to arise by chance. So that is true. The other point of what are the amino acids that are there, I actually have an image which I didn't put in the presentation that says there is significantly more abiotic, or these amino acids that don't require biosynthesis, right, in the central spheres than there are in all these other spheres. So that's a sign of some sort, but I guess I would see a sign in almost anything. So
Yeah. So, sorry, one more short.
We need to move on.
Okay,
for
sorry.
the sake of time, sorry.
I'm going to be around. So
Thank you very much, Yana. We
Do I
thank
do
Yana
anything?
again for such a wonderful keynote lecture.